All right, so we're in section 6.3 today, and we're still talking about volumes, which is what we talked about in 6.2. But we're going to look at a different method for computing volumes. Specifically, this applies to volumes of solids of revolution. In 6.2, we talked about solids of revolution and using our cross-sectional area formula for computing the volume, we found that we could think of those cross sections as disks or washers, and we frequently call that method the disk method or the washer method for finding those volumes of solids of revolution. It turns out that as useful as that technique is, there are certain cases where computing the volume of a solid of revolution using either disks or washers is actually very difficult. And an example of a case where that would be hard to do is this one right here. So what I'm looking at in this picture is a region bounded by this function up here, y equals 2x squared minus x cubed. And we're thinking of it as bounded by that curve and the x-axis, I should say. So this blue region right here. We want to rotate that around with the y-axis to obtain a solid of revolution, and then what we want to do is find the volume of that solid. So if we're using the washer method for this, then what I would be doing is I would be thinking of this little rectangle right here as being drawn perpendicular to the axis of rotation. So if I'm or axis of revolution. If I'm revolving around the y-axis, then you can see that this rectangle kind of points perpendicularly to the y-axis. That's what would generate a washer, because if you can picture this rotating around that axis, you're going to get that washer, that disc with a hole in it. So that's kind of what we would be looking at using the method of 6.2. But the tricky thing, if we're going to approach the problem this way, is the washer method. Before, we would find an inner radius and an outer radius, each of which came from its own function that was bounding this region. And here, both the inner radius and the outer radius are coming from the same curve, just different parts of the same curve. It turns out that makes it a lot more difficult to use that washer method in a case like this. Partially because if we're going to be rotating this region or evolving this region about the y-axis, then we have to integrate with respect to y, which means if I have this function here where y is given as a function of x, I need to solve this for x so that I can end up with x as a function of y instead, so that the integration works correctly. But this is very difficult to solve for x. And if you want, you can try it. How would you isolate an x in this polynomial here? That ends up being too difficult for what we're trying to do in this section. So we're going to come up with a different approach which will compute the same volume that we're looking for, but avoids that problem. And really, kind of like we said, the issue is that this rectangle is being drawn perpendicular to your axis of rotation. So let's consider instead what would happen if you drew a rectangle within this region that was parallel to your axis of rotation. So in this case, instead of looking at horizontal rectangles, I'd be looking at vertical rectangles. Think about what shape or what solid that one rectangle, when drawn vertically, would create when it's rotated about this vertical axis, this y-axis. You don't have to visualize it in your head because I have it right here. So here is the same curve that we were looking at up here, right? Y equals 2x squared minus x cubed. And if you can see this, there's a red rectangle drawn right here. When we rotate that red rectangle about the y-axis, it's going to trace out this cylindrical shell. And when I say cylindrical shell, what we're going to think of that as is a cylinder, like a solid circular cylinder, with a smaller circular cylinder kind of cored out of the middle of that larger cylinder. So it's like we took a core out of it. Okay, so you can see that this little rectangle would create that cylindrical shell. Now, coming over here, this is just like a general cylindrical shell. I want to do a little bit of work with this. Namely, what we're trying to do is figure out how to compute the volume of a cylindrical shell. And it's not difficult if you think of it as a larger cylinder with a smaller cylinder removed from its center. Because if we can find the volume of the larger cylinder, all we would have to do is subtract from that the volume of the smaller cylinder, and what we're left with is the volume of the shell. So to name a couple of important dimensions on this thing, because this shell is kind of made up of a larger outer cylinder and a missing smaller inner cylinder, we need to know the radius of each one of those. So I'm going to let R1 represent the radius of the inner cylinder. It's the smaller radius. R2 is going to represent the radius of the outer cylinder. And then it turns out in this derivation, it's actually very helpful to work with not just R1 or R2, but the average or the mean of those two. So right here, I define R to be 1/2 times the sum of R1 plus R2. That's the same thing as the average of R1 and R2. And being the average of two numbers, that would give us something that is exactly between those two numbers. So that radius would go from the center of your cylindrical shell right here to the middle of this thickness that makes up the kind of the rim of that shell. Okay. Also relevant to our derivation that we're going to do here in a moment is the actual thickness of the shell itself, which I'm going to call delta R. But in terms of the radii, delta R would just be the larger radius minus the smaller radius. That would leave you with that thickness. So I'm going to define right here, delta R is going to equal R2 minus R1. It's the difference between those two radii. Okay, and then H is exactly what you would expect it to be. It's the height of that cylindrical shell. So how do we find the volume of this? Well, like I said before, the volume of this shell is just the volume of the larger outer cylinder minus the volume of the smaller inner cylinder. We're going to do that on this next page. So up here at the top, I'm going to let V2 represent the volume of the outer cylinder. V1 is the volume of the inner cylinder. I think I could zoom in just a little bit there. Okay. So how do you find these volumes? Well, the volume of any cylinder is pi r squared h. And for our outer cylinder, the radius is called R2, so this would be pi r2 squared h. The volume of the inner cylinder then would look like pi r1 squared h. Now notice both of these terms have a pi and an h in them, so I can factor the pi and the h out separately. And once I do that, I see that I'm left with a difference of squares here. By this point, you should be intimately familiar with how these things factor. Shouldn't require any thought at this point. This is something you've done over and over and over again. So this would factor to R2 plus R1 times R2 minus R1. That's what that difference of squares is going to look like. And right away, this R2 plus R1 and this R2 minus R1 are starting to look kind of like things we've already defined. For example, if this R2 plus R1 were multiplied by 1/2 or divided by 2, that's how we defined R. Remember, that was the average of those two radii, and that's a value that we've given a label to. So if I divide this by 2, I can, in a later step, label this entire thing R. But I can't just go dividing things by 2 without compensating for that somewhere. So if I'm going to divide this by 2 here, I'd like to then multiply the entire expression by 2 so that these two things would end up canceling out to get me back to my previous step. Okay, and then the only other thing that's happened from this step to this is that we've kind of switched the order of these two terms, which by the commutative property is totally fine to do. Relabeling a few things. I can write this volume as 2 pi, which is showing up here, times, like we said, this quotient here can be written as R, times H, times delta R. Remember, delta R was equal to R2 minus R1. Okay? And that's like a volume formula for a cylindrical shell. And a good way to remember that is by this. This is going to be helpful for what we do in this section. The volume is equal to circumference times height times thickness. Remember, the cylindrical shell that we're looking at, I'll go back to this picture, can be thought of as kind of like a washer or even like a circle on the top. And the radius, if I took the circle that kind of went right through the middle of that thickness so that the radius is just that R, the circumference of that circle on top would be 2 pi R. That's the circumference formula for a circle. Notice that shows up right here. So 2 pi R, that's circumference, times height, that's H, times thickness is what delta R represented. That's an easier way of remembering the volume formula for one of these cylindrical shells. Okay, so how are we going to use these cylindrical shells to come up with the volume of a solid of revolution now? So here is an example of another curve, y equals f of x, over some interval on the x-axis, a, b. And this time what we want to do is rotate this thing not about the x-axis, but about the y-axis. So you can see the arrow there indicating where we're rotating. If I were to rotate that thing around or about the y-axis, I'm going to get a solid of revolution that looks kind of like this right here. Okay, and what I want to do is take my interval AB and partition it up into subintervals, which hopefully by now is starting to feel like a common theme in this class. Whenever we talk about taking an interval and partitioning it up into subintervals, that should clue you into the fact that we're starting to work ourselves towards a definite integral, because that's going to lead us to a Riemann sum. We're going to apply a limit to that. That gives us a definite integral. Okay, but if I partitioned AB into all these little subintervals, and then for each of those subintervals, I construct a little rectangle like you do when you define the definite integral in Calculus 1. And for this rectangle, the width is still going to be thought of as delta x, so that's familiar. And then if you recall, when we do the rectangular approximation method in Calculus 1, we say that you need to choose some sample point in that subinterval, which you then plug into your function to determine the height of that rectangle. And for this derivation, we don't want to just let that be any random point. We're going to be very intentional and choose the midpoint of that subinterval as the value that we're going to plug in to get that approximating rectangle. Okay, now if you take that rectangle and you rotate it about the y-axis, it's going to generate one of those cylindrical shells. And then if you go and do that same thing for each subinterval that you define in this interval AB, you're going to get these, what I kind of like to think of as nested cylindrical shells. So they're kind of like, contained within each other. If I partition AB into a lot of subintervals, you're going to end up with a lot of these cylindrical shells. So you can see, here we've only chosen, 1, 2, 3, 4, 5 shells, but here we have probably, 10, 12 shells. There's significantly more here than there are here. And I can see that the solid that I'm getting from these shells looks more closely like this actual solid that we want to find the volume of than this does. So that's kind of your clue that if you partition AB up into more and more subintervals, giving you more and more cylindrical shells, the volume of this approximating solid is going to get better and better. And so we would expect that if you applied a limit to the number of those subintervals as the number goes to infinity, that becomes an accurate volume and not just an approximation anymore. So that's what all of this is kind of describing right here. And if I start with the approximation, let's let VI represent the volume of just one of those shells where it came from a rectangle over the ith subinterval. So xi minus 1 to xi, that little subinterval right there. What would the volume of that be? Well, we just derived the volume of a cylindrical shell up above, and we found that it was equal to circumference times the height times the thickness. And in our case, the circumference is 2 pi xi bar. And the reason for that is because, again, this rectangle is going to be giving us the thickness of that shell. And if I chose the midpoint of that rectangle to determine its height, that midpoint is exactly the average of the inner radius and the outer radius of that shell. Hopefully you're able to see that. Well, remember, that midpoint showed up in our formula, so that would mean that this circumference that we want here is 2 pi xi bar. But then by also using xi bar to determine the height of our rectangle, that shows up here as well. So xi bar is showing up in two places, fxi bar right here. And then delta x the width of that subinterval right there, is going to be the thickness of that cylindrical shell, and so delta x represents our thickness. And right away, this is looking like the kind of thing that we put into a Riemann sum to come up with a definite integral, which is exactly what we want to do. This is the volume of only one of those shells, but I want to sum the volume of all of these cylindrical shells to get the total volume that I'm trying to get. So if I do that, if I sum this from I equals 1 to n, representing all n subintervals, then I get a good approximation for the volume of my solid, okay? Then, like we were saying before, if we apply a limit to that summation there so that our approximation gets better and better, this thing is going to turn into a definite integral. And this is what it would look like. So the integral from a to b, remember that's the interval over which we're defining our region, of 2 pi x f of x dx. This would give me the volume that I'm looking for. Now, I would recommend not memorizing this particular formula, because this is specifically going to give you the volume of the solid of revolution that's specifically described this way. It would only work if this is a region that's bounded above by some curve y equals f of x and below by the x-axis, and if we're rotating that about the y-axis, okay? What if the region is not bounded below by the x-axis, but what if it's bounded above by a curve and below by another curve? Or what if we are rotating it about the x-axis or some line like x equals 3 or something like that? In those cases, this formula wouldn't really work if we used it directly, but it will work if we think of it more generally as the integral from a to b of the circumference times the height times the thickness, just like how we, are thinking about the volume of a cylindrical shell, where we understand the circumference to be 2 pi times x. And what is x really? X, in this example right here, came from that xi bar right there, but we're thinking of that as the distance between your approximating rectangle and the axis that you're rotating around. So if you choose a different axis, that xi bar there can be something else, and we'll look at what that could possibly be. And then also we have the height of our rectangle right here, f of x. But if our region is a region bounded by two curves, that height might look a little bit different. What's going to be helpful is to just think of this integrand as circumference times height times thickness, and then we'll kind of adapt to whatever that means according to the region that we're trying to find or trying to work with in our problem. Okay, so this whole video is just on the derivation of this method, which we call the shell method, or volume by cylindrical shells. In the next video, we're going to start looking at some examples where we can use this.